we come to one of the more important topics of the chapter, which is instruction code. So the chapter itself, if you remember, is instruction representation, as in my high level program or code gets converted to a bunch of instructions which my registers are capable of comprehending, and those instructions are what we are learning about, the language or the syntax for representing those instructions, the notation, the keywords, and so on. So instruction code refers to the bunch of instructions. So that's what we're going to be looking at. So a quick intro. Program, as you know, is basically a set of instructions which tell you what operations have to be performed on which operands and in which sequence. This is what we can infer from a program. Now, what is an instruction code? It's a group of bits that tell the computer to perform a specific operation, that is a sequence of micro operations. So if I say add x comma y, that is an instruction. So it tells me what operation has to be performed, that is add, and it tells me which operands I have to use, x comma y. Thirdly, it can also be broken down into a set of micro operations like fetch x, fetch y, add x comma y, store result in z, or whatever. So an instruction is something which tells you what operation should be performed on which operands. It either gives you the operands directly or the location, the memory address of the operands, and it is then broken down into a sequence of micro operations and they are executed. So that's what an instruction is. So an instruction code refers to an instruction which is written in that specific language, like register transfer language, which the register is capable of understanding, which the control unit is capable of understanding. Now the instruction statement itself is divided into multiple parts. You have the opcode, operation code, operand, address, addressing mode, and so on. So addressing mode is in itself not a part of the instruction, as in when you take an instruction, the instruction again is encoded into binary form. It is also present in the form of zeros and ones. So the other three parts like opcode, operand, and address, they are present in the instruction. So if I take a 16-bit instruction, let's say I have a 16-digit number, binary number, I can say the first 4 digits represent the operation code, the next 8 digits represent the operand, the address of the operand, the next 4 digits tell me what operation should be performed, or something like that. The addressing mode as such is not always a part of that. It is something you infer from the way the instruction has been written, or from the vector. So I'll give you an example, it will be clearer. So as of now, what I want you to understand is, you know what an instruction is, and instructions are also converted into binary digits, bits, bytes, vectors, and that is how they are also stored inside the system. Okay, so again, if you take a 16-bit register, it contains 16 binary digits or bits, and that 16 bits represent one instruction, where you can see that the first 12 bits represent the address, the memory address of the operand, and the last 4 bits are the opcode. So for example, if my opcode is 0000, it represents a specific operation, for example the add operation. If the opcode is 0010, it could refer to the shift operation. So for every code there is a corresponding operation. So depending on what the last 4 digits, the digits stored in location 12, 13, 14, 15 are, the control unit will direct my ALU to perform that specific operation, and perform that operation on whom? On the operand. And where is the operand? At a specific memory location or address, which is stored in these first 12 locations. So that's what that is how you decode an instruction. So this instruction consists of 2 parts, an opcode and an address. There could be instructions where you have the mode, opcode, and address, and so on. So this is what I meant when I said the mode is not always directly a part of the instruction. So it depends from architecture to architecture, it depends from system to system, depends from the hardware used to the hardware used. In some systems, the instruction just consists of operation code and the address. Sometimes you have the mode, operation code and address, and so on. So those are different types of representing the instruction. So depending upon what architecture that system follows, the control unit will accordingly decode that instruction and execute it accordingly. So if I have a system which follows this structure, then my CU knows that any instruction that comes to it should be divided into opcode and address only in the ratio 4 bits for opcode, remaining 12 for address. So that is how it will split that 16-bit vector, and it will take the first 4 bits, it will check what they are, it will find out what is the corresponding operation. The next 12 bits, it will figure out the location in the memory, it will take that operand from there and perform that operation. Similarly, if my system is one that uses this format of mode, opcode, address, then whenever I get a 16-bit instruction, my control unit will split it into 3 parts, 1 bit for the mode, 3 bits for the opcode, and the remaining 12 bits for the address, and again it will process it accordingly. So that is what we refer to by different addressing modes. We will be looking at addressing modes in a little more detail right now. So before we go into that, what is effective address is the address that can directly be used without modification. And in contrast to this, we have something called the indirect address. So I'll give you an example. So we are going to be looking at instructions here where you have 3 parts to any instruction. The first part is the mode, the second part is the opcode, and the third part is the address. So remember, inside a system, all of this will be binary, it will all be in zeros and ones. So if you have the word add here, inside the system there is a configuration corresponding to codes for every operation. So for example, if it says 000 equals add, then you will not find the letters ADD here, you will actually find the numbers 000. Similarly, you will not find 457 here, you will find the binary equivalent of that particular memory address. But for our understanding, here the actual values are given. So in any case, this is an instruction. This 1 bit refers to the mode. This is the opcode translated into what operation, and this is the memory address. So now, if now my CPU knows it belongs to an architecture where the instruction is divided into 3 parts. So it will divide the 16 bits into 3 parts like this first of all. Then it will look at the first part, which is the mode bit. So if the mode bit is 0, then it is a direct address instruction, meaning I will go to this address, I will take the operand from there and I will directly perform the operation. So it is like a single pointer in your C programming. So asterisk x means x is a memory location, you go to the location, you directly pick up whatever value is there and you add or subtract or print or whatever. So that's exactly what happens here. So this is 22 is where my instruction is stored. My CPU first takes the mode bit. The mode bit is a 0, meaning this is direct addressing. So it will check the address, it will go to that address 457, it finds the operand, it will directly take the operand, it sees what operation has to be performed, addition. So it will perform it and put that value in this register. AC stands for accumulator, which is a special purpose register, meaning it accumulates value. So whatever value is already in it, to that it will add the incoming value. So if AC has, let's say, a 5 and the operand value is 10, after this operation happens, the AC becomes 15. This is how direct addressing works. Now coming to indirect addressing, it's a very simple change. The mode bit is a 1. So the control unit realizes this is indirect addressing, which works like your double pointer. So you have a pointer to a pointer. So the first pointer takes you to a location. From that location you have a pointer to another location, and the second location is where you get your actual variable. That's what happens here. So this is my instruction. Again, my control unit sees a 1 here. It realizes this is indirect addressing. So it looks at this address 300. It goes to address 300. It finds the address 1350. Again it goes to the address 1350, there it finds the operand, it picks up the operand, then it reads what operation I have to perform, addition, so it adds and puts it in the accumulator register. So these are two addressing modes, direct addressing versus indirect addressing. Direct addressing is where your effective address is given. So if I go to this address, I will find my operand. Such an address is called the effective address. So here 457 is where my operand lies, so that's my effective address, that's directly given, so we call it the direct addressing. In indirect addressing, it's a double pointer kind of thing. You have the address of the address, so you have to do two tracings or you have to go to two addresses sequentially and then you find the operand. So, and how does the control unit figure out which mode is being used? With the help of this mode bit. If it's a 0, direct addressing. If it's a 1, indirect addressing.